Let's take a look at the next example. We want to determine the limits of integration. In example 4, we want to set up a triple integral for the volume of each solid region. The first one is the region in the first octant bounded above by the cylinder z equals 1 minus y squared and lying between the vertical planes x plus y equals to 1 and x plus y equals to 3. So we're asked to set up a volume integral to determine this volume. So we are looking for a triple integral over the surface dv, which we are hoping to write as an iterated integral. For the order of integration on this, let's go with, let's say, we'll do dz, dy, dx, dy. So we need to determine the bounds of integration. The textbook offers the graph of the surface. I've kind of sketched its projection onto the xy plane over here. First of all, let's take a look at z. They say that we have to be in the octant, the first octant. So we know it's going to lie above z equals to 0. So in terms of our limits of integration, when we're integrating with respect to dz, we know z will be greater than 0, and we know z is going to lie below 1 minus y squared. That tells us that 0 is less than or equal to z is less than or equal to 1 minus y squared. So our upper bound here is going to be 1 minus y squared. If we look at x, it has to be between x plus y equals to 1 and x plus y equals to 3. If we're going to integrate next with respect to x, then we can't have functions of x for our bounds here. We would need functions of y. So let's take each of these two and solve them for x. The first one would say that x is equal to y minus 1. The second one would tell us that x is equal to, excuse me, that's backwards. Should be 1 minus y, if we can do algebra. And then the next one would be 3 minus y. If we look at the projection of our region, what we see is that the upper bound for our x values here is going to be this function. X is going to be less than or equal to 3 minus y, but it's further out of the page than this function, the 1 minus y. So our bounds for x are going to be from 1 minus y to 3 minus y. And then the last thing we need is the bounds for our y variable. If we look at this region on the y-axis, these bounds will go from y equals to 0 to y equals to 1. So this would be our iterated integral that would give the volume of the region in part A. In part B, we want to set up a volume integral for the upper hemisphere given by z equals the square root of 1 minus x squared minus y squared. If we wanted to take a look and see what this region would look like, it's just that upper half sphere. Let's go ahead and set up the volume integral for this. So we're looking for the volume of the upper half hemisphere, whose equation is given by, if I have it written down, z equals the square root of 1 minus x squared minus y squared. And let's go ahead and we'll set it up. if we look at the projection of this, again, look at the projection of the surface into the xy plane. Here's our z. If we do that, what we're going to see is a circle. And that being a circle of radius 1. Because we're looking at the upper half hemisphere, or hemisphere, I shouldn't say half hemisphere. Hemisphere already implies that it's half of a sphere. We want the volume of this, so we're going to set up a triple integral over the surface, dv. And for our order of integration this time, let's do dz dx dy. Because it has to lie above the xy plane, we know that z is going to be greater than 0. And it's going to lie below the curve square root of 1 minus x squared minus y squared. So our bounds for z are going to go from 0 to the square root of 1 minus x squared minus y squared. If we look at the projection of this region onto the xy plane, then z would be equal to 0, which would give us that the 0 is equal to the square root of 1 minus x squared minus y squared. Could square both sides. This would give us a circle. Again, as we said before, if I move the x and the y squared terms to the other side, we get x squared plus y squared equals to 1. If we are going to integrate with respect to the dx, then we can't have x for our bounds. We need a function of y. So let's go ahead and solve this for x. X squared is equal to 1 minus y squared. If we take the square root, we get x equals plus or minus the square root of 1 minus x squared. This portion here would be the positive branch in the xy plane of the radical, and the part back here, that would be the negative branch of the radical. We see that if we look at our values of x, our values of x are bigger than the negative of the square root in this projected surface on the xy plane, but they're less than the positive of that root. And then lastly, we just need our bounds for the y variable. If we look at on the y-axis, the y values go from -1 to +1. So there you have it. This would be our triple integral that would give us the volume of the hemisphere. We will do one more region. Let's find the volume of the region bounded below the paraboloid z equals x squared plus y squared, and above the sphere x squared plus y squared plus z squared is equal to 6. If we wanted to look at that region, we can see that it's going to be above the paraboloid, yet it's going to be below the sphere. Let's work this one out. So we're looking for it to be below z equals x squared plus y squared, yet it has to be above x squared plus y squared plus z squared equals 2 to 6. And let me just make sure I have that correct. So we want it bounded below the paraboloid. I believe we have a typo here. Below the paraboloid, but yet above the sphere. Should actually be below the sphere and above the paraboloid. So, typo in the textbook, actually. And let me just quickly, before I try to jump around too quickly here, take a look at the region that's shaded here. If you look at the sphere, this sphere is our x squared plus y squared equals to 6. That's a sphere with, or is that correct? Hold on one second. I got myself reversed here.